Everything that moves will be robotic someday, and it will be soon. You know, the idea that we'll be pushing around a lawnmower is already kind of silly. You know, maybe people do it because it's fun, but there's no need to. And every car is going to be robotic. Humanoid robots, the technology necessary to make it possible is just around the corner. And so everything that moves will be robotic. And they'll learn how to be a robot in Omniverse Cosmos, and will generate all these physically plausible futures, and the robots will learn from them, and then they'll come into the physical world, and it's exactly the same. In the early 90s, when we first started the company, we observed that in a software program, inside it, there are just a few lines of code, maybe 10% of the code does 99% of the processing. And that 99% of the processing could be done in parallel. However, the other 90% of the code has to be done sequentially. It turns out that the proper computer, the perfect computer, is one that could do sequential processing and parallel processing, not just one or the other.
Why gaming first?
The video games requires parallel processing for processing 3D graphics. And we chose video games because, one, we loved the application. It's a simulation of virtual worlds, and who doesn't want to go to virtual worlds? And we had the good observation that video games has potential to be the largest market for entertainment ever. And it turned out to be true. A GPU is like a time machine because it lets you see the future sooner. One of the most amazing things anybody's ever said to me was a quantum chemistry scientist. He said, Jensen, because of Nvidia's work, I can do my life's work in my lifetime. That's time travel. He was able to do something that was beyond his lifetime, within his lifetime. And that's because we make applications run so much faster. And you get to see the future. And so when you're doing weather prediction, for example, you're seeing the future. When you're doing a simulation, a virtual city with virtual traffic, and we're simulating our self-driving car through that virtual city, we're doing time travel.
So parallel processing takes...
Fundamentally, the reason why I was certain that CUDA was going to be successful, and we put the whole company behind it, was because fundamentally, our GPU was going to be the highest volume parallel processors built in the world because the market of video games was so large. And so this architecture has a good chance of reaching many people. And we were frustrated by a whole bunch of early developments internally with respect to our computer vision effort and getting CUDA to be able to do it. And all of a sudden, we saw AlexNet, this new algorithm that is completely different than computer vision algorithms before it. But the big breakthrough, I would say, is when we saw AlexNet, we asked ourselves, how far can AlexNet go? If it can do this with computer vision, how far can it go? And if it could go to the limits of what we think it could go, the type of problems it could solve, what would it mean for the computer industry, and what would it mean for the computer architecture? And we rightfully reasoned that if machine learning, if these deep learning architecture can scale, the vast majority of machine learning problems could be represented with deep neural networks. And the type of problems we could solve with machine learning is so vast that it has the potential of reshaping the computer industry altogether. All things that we pursue, first you have to have core beliefs. You have to reason from your best principles. And ideally you're reasoning from principles of either physics or deep understanding of the industry or deep understanding of the science, wherever you're reasoning from. You reason from first principles, and at some point you have to believe something. And if those principles don't change and the assumptions don't change, then there's no reason to change your core beliefs. And then along the way, there's always some evidence of success and that you're leading in the right direction. And sometimes you go a long time without evidence of success, and you might have to course correct a little. But the evidence comes, and And if you feel like you're going in the right direction, we just keep on going. The question of why did we stay so committed for so long, the answer is actually the opposite. There was no reason to not be committed because we believed it. Our first discussion was about accelerated computing, parallel computing versus general purpose computing. We would add two of those processors together and we would do accelerated computing. And I continue to believe that today. The second was the recognition that these deep learning networks, these DNNs that came to the public during 2012, these deep neural networks have the ability to learn patterns and relationships from a whole bunch of different types of data, and that it can learn more and more nuanced features if it could be larger and larger. And it's easier to make them larger and larger, just make them deeper and deeper, or wider and wider. And so the scalability of the architecture is empirically true. The fact that model size and the data size being larger and larger, you can learn more knowledge, is also true, empirically true. And so if that's the case, you could, what are the limits? There's not, unless there's a physical limit or an architectural limit or a mathematical limit, and it was never found. And so we believed that you could scale it. Then the only other question is, what can you learn from data? What can you learn from experience? Data is basically digital versions of human experience. And so what can you learn? We've now demonstrated that AI or deep learning has the ability to learn almost any modality of data, and it can translate to any modality of data. And so what does that mean? You can go from text to text, right? Summarize a paragraph. You can go from text to text, translate from language to language. You can go from text to images, that's image generation. You can go from images to text, that's captioning. You can even go from amino acid sequences to protein structures. The last 10 years was really about the science of AI. The next 10 years, we're going to have plenty of science of AI, but the next 10 years is going to be the application science of AI, the fundamental science versus the application science. And so the applied research, the application side of AI now becomes, how can I apply AI to digital biology? How can I apply AI to climate technology? How can I apply AI to agriculture, to fishery, to robotics, to transportation, optimizing logistics? How can I apply AI to, teaching? How do I apply AI to, podcasting, right? And so, okay. And so now let's come into the physical world, the world model. We need a foundation model, just like we need ChatGPT had a core foundation model. That was the breakthrough. In order for robotics to be smart about the physical world, it has to understand things like gravity, friction, inertia, geometric and spatial awareness. It has to understand that an object is sitting there even when I looked away. When I come back, it's still sitting there, object permanence. It has to understand cause and effect. If I tip it, it'll fall over. And so these kind of physical common sense, if you will, has to be captured or encoded into a world foundation model so that the AI has world common sense. Okay. And so we have to go, somebody has to go create that. And that's what we did with Cosmos. We created a world language model. Just like ChatGPT was a language model, this is a world model. The second thing we have to go do is we have to do the same thing that we did with PDFs and context and grounding it with ground truth. And so the way we augment Cosmos with ground truth is with physical simulations. Because Omniverse uses physics simulation, which is based on principled solvers. The mathematics is Newtonian physics. It's the math we know. Okay, all of the fundamental laws of physics we've understood for a very long time, and it's captured into Omniverse. That's why Omniverse is a simulator. And using the simulator to ground or to condition Cosmos, we can now generate an infinite number of stories of the future, and they're grounded on physical truth. Just like between PDF or search plus ChatGPT, we can generate an infinite amount of interesting things, answer a whole bunch of interesting questions, the combination of Omniverse plus Cosmos, you could do that for the physical world. A version of generating fake information, fake news or fake images or whatever it is. Of course, impersonation. It does such a good job pretending to be a human. It could do an incredibly good job pretending to be a specific human. And so the spectrum of areas that we have to be concerned about is fairly clear, and there's a lot of people who are working on it. There's some of the stuff related to AI safety requires deep research and deep engineering, and that's simply it wants to do the right thing. It just didn't perform it right, and as a result, hurt somebody. For example, a self-driving car that wants to drive nicely and drive properly, and just somehow the sensor broke down, or it didn't detect something, or made it too aggressive turn, or whatever it is. It did it poorly. It did it wrongly, and so that's a whole bunch of engineering that has to be done to make sure that AI safety is upheld by making sure that the product functioned properly. And then lastly, what happens if the AI wants to do a good job, but the system failed? Meaning the AI wanted to stop something from happening, and it turned out just when it wanted to do it, the machine broke down. And so this is no different than a flight computer inside a plane having 3 versions of them, and then so there's triple redundancy inside the system, inside autopilots, and then you have 2 pilots, and then you have air traffic control, and then you have other pilots watching out for these pilots. And so the AI safety systems has to be architected as a community such that these AIs function properly. When they don't function properly, they don't put people in harm's way, and that there's sufficiently safety and security systems all around them to make sure that we keep AI safe. And so in the end is about how much work you can get done within the limitations of the energy that you have. And so that's a physical limit. And the laws of physics about transporting information and transporting bits, flipping bits and transporting bits, at the end of the day, the energy it takes to do that limits what we can get done. And the amount of energy that we have limits what we can get done. We're far from having any fundamental limits that keep us from advancing. In the meantime, we seek to build better, more energy efficient computers. This little computer, the big version of it was $250,000.
Can I pick it up?
Yeah. That's little baby digits. Yeah. This is an AI supercomputer. The version that I delivered, this is just a prototype, so it's a mock-up. And so the very first version was DGX-1 I delivered to OpenAI in 2016, and that was $250,000, 10,000 times more power, more energy necessary than this version. And this version has 6 times more performance. Wow. I know, it's incredible.
We're in a whole new world.
And it's only since 2016. And so 8 years later, we've increased the energy efficiency of computing by 10,000 times. And imagine if we became 10,000 times more energy efficient, or if a car was 10,000 times more energy efficient, or electric light bulb was 10,000 times more energy efficient. Our light bulb would be right now, instead of 100 watts, 10,000 times less, producing the same illumination. Yeah, and so the energy efficiency of computing, particularly for AI computing that we've been working on, has advanced incredibly, and that's essential because we want to create more intelligent systems, and we want to use more computation to be smarter, and so energy efficiency to do the work is our number one priority.